Then we'll look at how that's used in image and video compression. I'll give you a real life example of SVD. Okay, now, before we begin with the actual topic, you guys should remember that the norm of a LP norm of a matrix is defined as the maximum of the LP norm of the vector AX, where the LP norm of the vector X is 1. Okay, so this is the definition of the norm of a matrix. It's an in-use norm based on the definition of the norm of a vector, LP norm of a vector, you know the definition, and then this is the corresponding definition of the matrix norm. Another fact that you guys should remember, and we did this with proof, if U is a unitary matrix, the unitary matrices preserve norms. Okay, so U is a unitary matrix here, and so X is a vector. The LP norm of the product UX is equal to the LP norm of X. Okay, this is for a vector, so the unitary matrix is preserving the norm. In other words, pre-multiplication with U does not affect the length. Likewise, UA equals LP norm of UA equals LP norm of A. Again, the norm of this matrix is preserved, even if you pre-multiply with a unitary matrix. We have seen this before. Okay, now we know that SVD of the matrix A, we assume that M is greater than or equal to N, is U sigma B transpose. Okay, and we have seen that we can break down this matrix A into a summation I equals 1 through N of sigma I UI VI transpose. Okay. You guys remember all of this?
Yes, Dr. Das.
Okay. Now, let's consider the L2 norm of a diagonal matrix. Okay. So this is a diagonal matrix, sigma, and these are the diagonal elements, lowercase sigma 2 until lowercase sigma n, and this is a concise way of representing that, equals diag of sigma I. And just to make this sigma look like the sigma matrix of SVD, I have made sigma 1, I'm assuming that sigma 1 is greater than or equal to sigma 2, is greater than or equal to sigma 3, and so on until sigma n, and they're all greater than or equal to 0. These are all non-negative, and this is sigma 1 is the highest, sigma 2 is the next highest, and so on. Okay, so this is my diagonal matrix. Now, this is just a convenient assumption. It might not be the case. Okay, and now I'm taking a vector x, x1, x2 until xn. Okay, and then I take the product sigma x. Sigma x equals, I do the multiplication, it's sigma 1 x1, sigma 2 x2 until sigma n xn. Okay, now what's the L2 norm, squared L2 norm of x? It's simply x1 squared plus x2 squared until xn squared, right? Likewise, what's the L2 norm of sigma x of this vector? It's sigma 1 squared x1 squared plus sigma 2 squared x2 squared all the way until sigma n squared xn squared, correct? So these are the norms of x and sigma x, where sigma is a diagonal matrix. Now, we know that the LP norm of the matrix, of any matrix, is equal to max with norm of x equals 1 the maximum of sigma x, maximum of the LP norm of the vector sigma x, right? So this is the definition. I just kicked in the definition of a matrix norm from, and then replaced A with sigma. Okay, so here's my problem. I want to restrict myself to an x. Okay, now I'm considering L2 norm. So P equals 2. By default, P equals 2, the L2 norm or the Euclidean norm. Okay, so what I'm doing here is I'm restricting myself to x's such that the squared L2 norm is equal to 1, x1 squared plus x2 squared until xn squared equals 1. In other words, the L2 norm of this is also of x is also equal to 1. And then I want to maximize this. So I'm restricting myself to this. This is equivalent to this. And then I want to maximize, instead of maximizing this, I'm just maximizing the square. And P equals 2, remember. So what sigma x squared is, we just saw this, equals sigma 1 squared x1 squared plus sigma 2 squared x2 squared until sigma n squared xn squared. Also, which is highest? Sigma 1. Numerically, it's the largest, right? Then sigma 2, then sigma 3, and sigma n is the smallest. What should my vector x be? Anyone? I should simply let x1 be equal to 1 and all the other x's be equal to 0, correct? So I amplify this term. This term becomes sigma 1 square. And I know that sigma 1 square is more than sigma 2 square, and which is more than sigma 3 square. So all of these sigma 2 until sigma n, these are all smaller than sigma 1, right? So sigma 1 square, I give, this is the one with the highest weight of all the terms. And if I make this x1 1 and all the others 0, then I'll be maximizing this L2 norm of sigma x squared, correct? So this is my solution. Whence, what's the value of this? I just replace these values x1 equals 1 and x2 2 through xn equals 0 here. So I get, what's the value of this then? The maximum value, that's, I set this equal 1 and everything else 0. So this is sigma 1 squared, right? And this is the maximum. Sigma 1 squared is the maximum of norm of sigma x squared. Whence, what is this? Norm of sigma? The norm of sigma x is square root of this, so sigma 1, correct? And so what's the norm of sigma? This lowercase sigma 1. Are you guys with me so far?
Yes, Dr. Ross.
Anyone else? Okay. So now here's an example. Now this one is not sorted in that manner. Okay, this is just another matrix D. What's the L2 norm of this matrix? I want you guys to answer.
4.
What's the L2 norm of this matrix?
Oh.
What is the L2 norm of this matrix? It should be 4, correct? Numerically, the highest. Okay. 4 is the L2 norm. Okay. I'll let you think why, but it is the L2 norm. And at the end, I have a MATLAB demo. Okay, now, so the L2 norm of a matrix A is sigma 1. This is the first singular value of A. Okay, let's prove it. So L2 norm of A is equal to L2 norm of U sigma V transpose. Agreed?
Yes.
Now, U is what kind of a matrix? A unitary matrix. V is another unitary matrix, correct? So, what's one of the properties of unitary matrices? They preserve the norm. So, this is equal to, since U and V transpose will preserve the norm, so this is equal to norm of sigma, correct? So, the norm of A is the same as the norm of sigma. And what's the norm of sigma? Sigma is a diagonal matrix. Diagonal elements are sigma 1, sigma 2 until sigma n, right? So the highest value is sigma 1. So the norm, the L2 norm of a matrix A is simply the largest singular value. And by the way, this holds for L1 norm and L infinity. Actually, any p equals 1, 2, 3, 4, it will hold. But I just showed it to you for the L2 norm. Okay, are we kind of clear until now? Or if you have any questions, please ask.
It's clear, Dr. Das.
Okay.
Clear.
Now, low rank matrix approximation. So we are given this matrix A, which is an m by n matrix. Okay, and A tilde is the closest low rank approximation of A. Okay, we want a matrix A tilde which is of lower rank than A. What's the maximum rank of A? Let's say this is more than, m is more than n. Then the rank would be n, right? In general, the rank of A would be at most minimum of n and n. And so we have an R which is less than m and n. Maybe this is a 20 by 15 matrix. M is 20, n is 15, and we want R to be 10. So we want we are looking for a matrix A tilde which has a lower rank than A. But within this restriction, we want one that is the closest approximation to A. In other words, A tilde is the closest approximation of A, which is of rank R. So this is our goal. Okay. So what is A tilde then? This is the approach. We do the SVD of A, and then A is equal to 1 through n of sigma I ui vi transpose. And each ui vi transpose is a rank 1 matrix. Okay, now if you add two rank 1 matrices, you'll get at best a rank 2 matrix. If you add 3 rank 1 matrices, you can get a rank 3 matrix. Okay, and so each term here is a rank 1 matrix. Since we have n terms, the rank of A is up to n. If I had 4 terms here, instead of all n terms, then the rank of this summation would have been 4. Okay. Okay. So A tilde is equal to I equals 1 through R. R is less than m and n. So it's less than n of summation of sigma I ui vi transpose. So basically, I'm carrying out the summation not over all n terms, but over the first r terms. Okay, and this is my solution, A tilde. It's the closest low rank approximation of A. And the rank of A tilde, of course, because it's a summation of uppercase R rank 1 matrices, the rank of A tilde is R. Now I haven't defined what closest low rank approximation means. Okay. So this is my A and this is my A tilde. Okay, so A tilde, I'm looking for a low rank approximation of A. So the L2 norm of the difference I want to minimize. This is my A, and the error between A and X, the difference is A minus X. Its L2 norm is here, and this is what I want to minimize. And so I want to find this matrix X, but the matrix X, the rank should be equal to R. Actually, rank X less than equal to R would be fine. And this, when we do the minimization, the minimum value would be when X equals this A tilde. This is the Eckart-Young-Mirsky theorem. And we won't do the complete proof, but we'll do approximately we just have a feel of what the proof looks like. So I take the difference. I know that when I replace X with A tilde, I will be minimizing the norm of the difference between A and X. Right? So A minus A tilde equals, I replace A with this summation and A tilde with this summation. This is I equals 1 through n, this is I equals 1 through r. Okay, so what will happen? Terms will cancel out, right? But I'll be left with the first r terms of this will cancel out, and then I'll be left with r plus 1 through n. So this A minus A tilde equals summation I equals r plus 1 through n of sigma I ui vi transpose, which is equal to, if you write this in terms of matrices, U times diag. See, what I've done is, I've taken my sigma, the uppercase sigma, sigma 1, sigma 2 until sigma n, and then I've zeroed out all the terms I equals 1 through r. And then I've taken I equals r plus 1 through n, sigma r plus 1 through sigma n. This is the diagonal matrix now, times V transpose. Okay, and what's the L2 norm of this? Remember, how do we get the L2? What was the L2 norm of this?
Yes.
I looked at which one was numerically the highest, right? 4 was the highest. I took the absolute values of all the diagonal elements, right? And the largest was 4. And we also know that unitary matrices preserve norms. Okay, now so this is what I have, right? This is a diagonal matrix with a lot of zeros in the diagonal elements too, and only sigma r plus 1 until sigma n, these are the non-zero diagonal elements. The maximum of these is, remember that the sigmas are all sorted. Sigma 1 is more, then sigma 2, then sigma 3, and so on. This is the smallest. So which one of these is the highest?
Sigma R plus 1.
Exactly. And U is a unitary matrix. So if I take the L2 norm of A minus A tilde will be, since U and V transpose are both unitary matrices, I just have to look at the L2 norm of this diagonal matrix, which is equal to sigma R plus 1. Okay. So this will be sigma R plus 1. If I take any other matrix X, then I'll be getting a value which is more than sigma R plus 1. And if you have a really large matrix, okay, like an image, then it will turn out that if you take like R equals 50 or something, sigma 1 will be very high, then sigma 2, sigma 3, sigma 4, and then gradually as you proceed, you'll see that all these singular values, sigma 20, sigma 30, 35, they'll be really small, progressively really small quantities. Okay, and so the L2 norm of the difference will be really small then. Okay, and so this is a very good approximation. This A tilde, which is of rank R, is a very good approximation of A. Okay, and we will see how this is used in image compression. So let's take an image, and we'll assume that it's a grayscale image, M by N image, and it's a matrix. Okay, you see how an image is a matrix, right? I take the pixel values as the entries of the matrix. Now, unit cost equals cost of transmitting a single pixel. So we are measuring cost. We're going to transmit this image, either transmit or store, it doesn't matter. I'm just assuming that it's a transmission. So we are going to transmit the value of each pixel. So to transmit this entire image, the cost would be mn units, right? N times n, because we have this many pixels. Agreed?
Yes.
Okay. Now, here is the SVD of A. A equals this I equals 1 through n summation sigma I by di transpose. I do the SVD of this image A. And then I take a low rank approximation. I equals 1 through R sigma I by di transpose. So my claim is that this is a very good low rank approximation of A, right? And let's see how we put this into use, this new knowledge that we just got. So this is my image A. It contains n terms, and this is A tilde, which contains R terms. Now, if I were to, let's see what the cost is when I transmit this A tilde. Remember, this is M by N matrix. So what's the cost of transmitting A? M times N units, right? Now, sigma I is a scalar. UI is a M by 1 matrix, and VI transpose would be 1 by N. It would be a row vector. In other words, VI would be a N by 1 vector. Okay, so, and we have how many terms in the summation? R. So if I transmit this, what will be the total cost of transmission? The cost of transmitting each, the vectors UI, there are R terms. And if I transmit all the UIs, I'll get R times M units. Agreed? Because each is M by 1. Likewise, the cost of transmitting VIs would be how much? Since each VI is a n by 1 vector, okay, so each time I transmit a scalar quantity, maybe a floating point or whatever, I incur a unit cost. Okay, so I hope you guys are with me. So the cost of transmitting all these VIs, R of them, would be R times n units. And then the cost of transmitting the sigma I will be, since there are R of them that I need to transmit, it will be R units. So what's the total cost of transmission? I add them up together. R m plus n plus 1. So if I, instead of this, which would incur a cost of m by n, if I were to transmit a tilde, I would be incurring this many units of cost. Okay, so do I save any? I save any when this is less than m by n, or when R is less than mn divided by m plus n plus 1. In fact, if you take a large image, I don't know, 1000 by 500, you'll see that R can be very high. Okay, and so if you take like first 50 or 60 singular values, I'll show you visually today, you will get a very good image. This A tilde image would look very similar to A, but it would be a low rank approximation, and it would, if you were to transmit A tilde instead of A, you would get a lot of savings. Or if you were to store them, either way it's fine. Color image compression, maybe I'll skip this. Let's do video compression. So this is a sequence of stills from a scene. A0, A1, A2, A T at time instant T, and then T plus 1 until the scene gets switched to some other scene. So this is a video clip of same scene. Okay, so these are the images here visually. So transmission side, this is what the transmission side will do, and then we look at the receiving side. So first, transmit A0, the first image, uncompressed. Okay, and then for T equals 1, 2, 3, for these subsequent images, what we do is take AT and then subtract A0 from it, the first image that you transmitted. So this is the difference, AT minus A0 is delta AT. So the difference image is delta AT. So that AT equals, if you take A0 and add the delta AT back to it, you'll get AT, right? Now, but what we do is we compress this delta AT using SVD. Okay, and we get delta A tilde T. This is after the compression, we get delta A tilde T. Okay, then this one is transmitted. So this blue horizontal dotted line, not blue, it's a purple horizontal dashed line rather, is the barrier between transmission and receiving ends. And so we are transmitting A0 first, and then A delta A tilde 1, delta A tilde 2, delta A tilde 3, and so on. And since we're compressing this, so the cost of transmission of all these delta A tilde T is much lower than transmitting A1, A2, A3 directly. Okay, now why do we do this is we do this transmission. And so the transmitted sequences, first A0 is transmitted, and then all the difference images are compressed and then transmitted. Okay. So this, remember this figure, we'll actually look at it later again. So these are what are being transmitted. And there's a lot of savings in the cost. Now, it actually makes sense if, why do we take the difference images, is because here are two frames. Okay, this is A0, and this is A t for some other t equals 1, 2, 3, 4. Okay, and so this whole thing is basically the same. The only difference is this moving vehicle. So what will happen to the difference image? So we transmit this original image, and then we take the difference image, difference between this and this. You see, most of the image is identical. So this will contain a whole lot of zeros. Okay, a lot of zeros, this image. And so we don't have to transmit all these zeros, so that's why we do the compression. So we take the difference between this and this, which would be only this scar minus this scar, whatever we get, and we compress that difference, that's delta A tilde t, and then that's what we transmit. Okay, now what happens at the receiving end? So this is the transmitted sequence, which we saw earlier. Now, receiving end, let's see what happens. Here, A0 is received, right? Actually, let's look at this. A0 is received, okay, and then delta A tildes are being received. Okay, so instead of delta A, the actual difference image, we are getting a compressed version of this. And then what we do is we add this to A0 at the receiving end. A0 is the original image, and then what we do is, so this is the difference image, delta A tilde t, that is appearing here. And so we add the two together, we get approximately, this is an approximation of AT, A tilde. A tilde t is A0 plus delta A tilde t. Okay, so this is the reconstructed sequence. All these images will be of slightly inferior quality, but the difference will be will not be perceptible if the compression is done by the right way. Okay, so this is the first transmitted image. Okay, this is the whole schematic, and what's happening here is this is an image of a still house and some person who's running towards the house. Okay, so here what's being transmitted is the first time we transmit this whole thing, and then we take the difference between the next image with the original one, and that image is compressed and then transmitted, and then we reconstruct this. We assume that the compression doesn't deteriorate the quality of the difference image, and so we add the two together and we get a close approximation of AT for subsequent time frames. Okay, are you guys clear with video compression?
Yes.
Okay, so what I'll do now is any questions about this whole topic? Or I'll go to the demo. We will demo what we just learned. This one. Actually, so let me generate a matrix A equals around let's define M and N. M equals, let's say, 10, N equals 7, A equals rand M N minus 50. Okay, so this is my A. I generate a random matrix. And then, actually, before this, I have to demo the norms. Let me do this. Let's take x equals rand so this is x, and let me, okay. For better visualization. Okay, now I do A equals diag x. So I create this diagonal matrix. Okay, now what's the L2 norm of this diagonal matrix? Any guesses?
47.
Exactly. Norm A equals 47. In fact, L1 norm will be 47 too. L2 norm is 47, which is what we saw, and the infinite norm will also be 47. Okay. Now, what's the Frobenius norm of this? It's going to look different. Okay. The Frobenius norm of this will be, we have to take the squares of all of these, 25 square plus 7 square plus 25 square plus 38 square and so on, and then add them up together. So it will actually be the L2 norm of x. Norm x is 85.30. So this will be the Frobenius norm of A. Okay. Anyway, so this is for diagonal matrices. Now, let's go back here. So I'm generating a random matrix, a tall matrix, 10 by 7 matrix. Then U S V equals SVD A. I do the singular value decomposition. Okay, and then what I'll do is, let's call A tilde equal 0. Okay, now I initialize it to 0, then I'll be adding new terms to it. Okay, so for k equals 1 through min mn, what I do is A tilde equals A tilde plus, let me do one thing. So this S is a matrix, a diagonal matrix. I'll just take the diagonal elements of it. A tilde plus S sigma I. This is I. I generally avoid using I here because I is square root of -1 in MATLAB by default. But for understanding purposes, let's take SI star UI, so U column I star VI transpose, so V I transpose. So so this is I'm doing the summation here in this for loop. And by the way, I wouldn't have done it this way. I'd have avoided the for loop, but for your understanding, I'm using the for loop. Okay, what will happen is A tilde will become equal to A at the end. Okay, and so let's run it. So what's my A? This is my A. What is A tilde? Well, these are all zeros, right? So I can round it off. And A. The same answer, right?
Yeah.
Okay. Okay. Now, let's look at it a little further. Okay. S printf rank of A tilde is equal to suppose will be backslash. Now let me and we'll do a pause here. Now let me run it. What's rank of A tilde? This is the first iteration of the loop. Rank is 1, right? Because I just added one rank 1 matrix. Then, oops, what did I do? Next iteration, it's 2. I actually pressed run again, so it's going to run again, but never mind. Then 3 and 4, 5, 6, 7, 8, 6, 7, because the rank of A is 7. Rank of A is 7. Okay. Did you understand this? Now let's look at the norm. I hope this worked. Okay. So I am going to print the rank of this and the norm. Oh, never mind. Backslash n should be 0. Now look at the norm. Okay, this is the L2 norm. What's happening to delta norm? Decreasing, right?
Yes.
It became 0 because A and A tilde become absolutely equal. And we can do the same thing. Let's remove the pause and do it for a larger matrix. Actually, let's keep this. And what we'll do instead of this is display A and A tilde side by side. Okay. It's too big. But you can see that they're very different, right? Let's take a smaller one. Six by 5. So this is 6 by 5 until this point, negative 25 to 27. And this matrix looks totally different, right? Right?
Yes.
It's very different. Then the next iteration, this. Now it begins to look, let's see the negative 22.9 here, it's negative 25, and here at 27, here at 29, 48, 44. So now it's beginning to look similar. See that? Now it's very similar. In fact, this is the last iteration, I think. Yeah. See that? So it gradually looks more and more similar to this. Now,